May 30th, 1942. A conference room deep within the British War Office, Whitehall, London. Admiral Louis Mountbatten stood before a gathering of senior military planners, his words hanging in the air like an impossibility. If ports are not available, we may have to construct them in pieces and tow them in. The room erupted in laughter. Hoots and jeers greeted the suggestion from men who had spent decades studying naval warfare and military engineering. The very idea contradicted everything the assembled officers knew about harbour construction, about physics, about the impossibilities of the English Channel. Build an entire harbour from scratch, transport it across the most treacherous waterway in Europe, and assemble it under enemy fire within days. Madness. Yet in that moment of ridicule lay the seed of what would become the most audacious engineering triumph of the Second World War. A project so ambitious that it would rewrite the rules of amphibious warfare and shatter every assumption the German High Command held about Allied capabilities. The mathematics of D-Day's success were being written not in battle strategy alone, but in concrete and steel, in hydraulic systems and tidal calculations, in the revolutionary concept that impossibility was merely another engineering problem waiting for a solution. The catastrophe had arrived on August 19, 1942, on the blood-soaked beaches of Dieppe. Over 6,000 Allied troops, predominantly Canadian, had stormed ashore in Operation Jubilee, a raid designed to test German coastal defences and demonstrate Allied resolve. The assault turned into a massacre. German machine guns positioned in concrete bunkers atop white chalk cliffs cut down wave after wave of attacking soldiers. 27 Churchill tanks rumbled onto the shingle beach, every single one destroyed or abandoned. Of the 4,963 Canadians who embarked that morning, only 2,210 returned to England, many of them wounded. The final tally staggered military planners. Canadian casualties alone numbered 3,367, including 916 dead and 1,946 prisoners of war. The Royal Navy lost 75 killed and 269 missing or captured. The Royal Air Force suffered 62 fatalities in the skies above Dieppe. German casualties barely exceeded 600. The raid lasted less than 9 hours from first landing to final evacuation. Those 9 hours taught the Allies the most expensive lesson of the war. Any future invasion of Fortress Europe would require capture of a major port to sustain the assault. Yet Dieppe proved beyond doubt that German defences made direct assault on a fortified harbour suicidal. Major General John Hamilton Roberts, commanding the 2nd Canadian Division, wrote in his after-action report discovered decades later in the National Archives. The strength of German port defences exceeded all intelligence estimates. Concrete casemates housing heavy artillery proved impervious to naval bombardment. Machine gun positions enjoyed interlocking fields of fire across every approach. The port facilities themselves were prepared for demolition at the first sign of attack. Even had we captured Dieppe intact, German counterattacks would have reclaimed it within 48 hours. The strategic paradox became inescapable. The Allies needed a port to invade Europe, but the Germans had fortified every port from Norway to the Spanish border with millions of tons of concrete and steel. Field Marshal Erwin Rommel, appointed Inspector General of Atlantic Wall Defences in late 1943, had transformed Adolf Hitler's propaganda boast into a genuine obstacle. By December 1943, Rommel had completed his 2-week inspection tour of Atlantic defences. His confidential assessment, preserved in German military archives, revealed his concerns. A basic concept for defence did not exist in any form, and any precautions taken did not meet the seriousness of the threatening major landing. His solution was characteristically aggressive. Rommel ordered the emplacement of millions of mines along potential invasion beaches. He demanded concrete pillboxes at every strategic point. He personally supervised the installation of beach obstacles designed to rip the hulls from landing craft. Rommel's asparagus, tall poles with sharpened tops, sprouted across fields behind the beaches to impale gliders and paratroopers. More critically for Allied planning, Rommel fortified the ports. In a secret memorandum to Hitler dated December 31st, 1943, Rommel wrote, "The focus of the enemy landing operation will probably be directed against 15th Army's sector. It is likely that the enemy's main concern will be to get the quickest possible possession of a port or ports capable of handling large ships." Hitler designated 11 major ports as Festungen, fortresses to be defended to the last man. Dunkirk, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire, the Gironde River estuary leading to Bordeaux, and the Channel Islands received priority for men and materials. Each fortress boasted heavy naval guns in reinforced concrete emplacements, artillery batteries covering every approach, anti-aircraft positions, minefields extending miles into the surrounding countryside, and garrisons prepared to fight to the death. The German defensive philosophy rested on an assumption so fundamental that no senior commander questioned it. An invasion force required capture of a major port within days of landing or face defeat through lack of supplies. This assumption had governed military planning since ancient times. Armies needed harbours for their supply ships, dockyards for repairs, cranes for unloading heavy equipment, warehouses for stores, and protection from storms that could scatter and destroy an invasion fleet. General Dwight D. Eisenhower, appointed Supreme Commander of the Allied Expeditionary Force, understood the problem with crystal clarity. In his personal diary entry from March 1943, he noted, "We face an impossible choice. Attack a heavily fortified port and suffer catastrophic casualties in the assault, or land on open beaches and watch our supply lines collapse within weeks. Either course leads to defeat. The alternative that emerges from failure at Dieppe may represent our only hope, though it defies all conventional military wisdom." What Eisenhower called the alternative had begun germinating in the minds of British engineers even before the Dieppe disaster. The concept traced its roots to 1917, when Winston Churchill, then First Lord of the Admiralty, had proposed using flat-bottomed barges and manufactured caissons to create an artificial harbour for planned operations against Dutch coastal islands. The Great War ended before the scheme could be tested, but Churchill never forgot the idea. In the spring of 1942, weeks before Dieppe, Churchill attended a conference where the impossibility of capturing a port came up for discussion. His response, recalled years later by multiple attendees, electrified the room. "If we cannot capture a port, we shall construct one and take it with us." The engineering challenges seemed insurmountable. How do you build a harbour capable of handling hundreds of cargo vessels? How do you transport thousands of tons of concrete and steel across open water? How do you assemble such a structure under enemy fire? How do you anchor it to the seabed in tidal waters that rise and fall 20 feet twice daily? How do you protect it from the violent storms that plague the English Channel? Each question spawned a dozen technical problems, yet the strategic necessity left no alternative. On May 30th, 1942, Churchill issued a directive to Admiral Mountbatten that would set in motion the most ambitious construction project of the war. The directive, preserved in the War Office archives, consisted of 60 words that changed military history. Piers for use on beaches. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves. Mountbatten assembled a team of Britain's finest engineers, naval architects and construction specialists. Their initial meetings at the Institution of Civil Engineers on Great George Street in Westminster produced more questions than answers. The sheer scale of what Churchill demanded seemed to violate the laws of physics and common sense. Lieutenant General Frederick Morgan, Chief of Staff to the Supreme Allied Commander, and his COSSAC planning team calculated the requirements. The artificial harbours would need capacity equivalent to the port of Dover, Britain's busiest cross-channel harbour. They must handle 12,000 tons of supplies daily, regardless of weather conditions. They must accommodate ships ranging from small landing craft to liberty ships of 10,000 tons displacement. They must provide shelter for vessels in seas up to Force 6 on the Beaufort scale. They must be assembled and operational within days of the initial invasion. The specifications alone filled hundreds of pages of technical documents. Civil engineer Hugh Ioris Hughes, a Welshman with extensive experience in harbour construction, submitted detailed plans for a floating harbour to the Royal Navy between June and August 1942. His design incorporated lessons learned from every harbour project of the previous century. Other engineers contributed specialised components. Royal Engineers Lieutenant Alan Beckett designed flexible steel roadways that could rise and fall with the tides while maintaining continuous connection to the shore. Naval architects proposed using obsolete merchant ships as instant breakwaters by scuttling them in predetermined positions. The most ambitious element involved massive concrete caissons, floating chambers that could be towed across the channel and sunk to form breakwaters. In October 1942, a combined operations conference codenamed Rattle took place at Largs in Scotland. There, Commodore John Hughes Hallett and Royal Navy Captain Tom Hussey presented the complete scheme to assembled military planners. The presentation lasted 4 hours and covered every technical aspect from tidal calculations to concrete mixing ratios. Skepticism dominated the initial reaction. American officers on the planning staff expressed particular doubt. One U.S. Navy captain, whose name appears in the conference minutes only as Captain S, voiced the consensus concern. "You're proposing to construct the equivalent of Dover Harbour, dismantle it into thousands of pieces, transport those pieces across the most dangerous waterway in the world, reassemble them under enemy artillery fire, and have the whole thing operational within a week. Gentlemen, I've been in the Navy for 25 years, and this is the most preposterous scheme I've ever encountered." Hughes Hallett's response, recorded verbatim in the conference transcript, demonstrated the desperation driving Allied planning. "Captain, you're absolutely correct. This scheme is preposterous. It defies every principle of harbour engineering. It requires technical innovations that don't yet exist. It demands industrial production on a scale that may exceed our capacity. Yet I ask you to consider the alternative. We either solve these preposterous problems, or we abandon any hope of invading Europe. The choice is that simple. A demonstration helped convince the skeptics. Commander Robert Grant conducted an impromptu experiment using the conference room sink, paper model ships, and a hairbrush to create waves. First, he placed the paper fleet in the sink and vigorously brushed the water. The paper ships capsized immediately. Then Grant inflated a Mae West lifebelt and placed it in the sink to represent a breakwater. The paper fleet sat inside the protected area. Again he applied the brush vigorously, creating waves that broke against the lifebelt. The paper ships remained afloat. The demonstration was crude, almost childish, yet it illustrated a fundamental truth. Protected water meant surviving ships. Surviving ships meant sustained supply. Sustained supply meant victory. The proposal went to Quebec in August 1943, where Churchill and President Franklin D. Roosevelt met with the combined chiefs of staff. Churchill presented the artificial harbour concept with characteristic eloquence. His opening statement, preserved in the conference minutes, captured the audacity of the plan. "Gentlemen, we propose to undertake the greatest construction project in military history, and to do so in complete secrecy, at breakneck speed, under constant threat of enemy detection. We will build 2 complete harbours, transport them across the Channel, and assemble them on hostile shores. The Germans will not believe such a thing possible. Their disbelief will be our greatest weapon." Roosevelt understood immediately. His engineering background, dating to his time as Assistant Secretary of the Navy, gave him appreciation for the technical challenges. Yet he also grasped the strategic necessity. The Joint Chiefs of Staff debated for 2 days. They examined every aspect of the plan, from concrete strength requirements to tidal predictions to German coastal artillery ranges. Finally, on September 2nd, 1943, they issued their decision. The combined chiefs of staff estimated that the artificial ports would need to handle 12,000 tons per day, exclusive of motor transport and in all weathers. On September 4th, the go-ahead was given to start work immediately on the harbours. Infighting between the War Office and the Admiralty over responsibility threatened to derail the project before construction even began. The Admiralty wanted complete control, arguing that anything floating fell under naval jurisdiction. The War Office countered that harbour construction was fundamentally an Army engineering responsibility. The dispute raged for 3 months, consuming countless planning meetings and delaying critical decisions. Only on December 15, 1943, did the Vice Chiefs of Staff intervene to impose a solution. The Admiralty would manage the block ships to be scuttled as breakwaters, the bombardons or floating outer breakwaters, and all assembly work on England's south coast. They would also survey the French coast, mark navigation channels, and tow all components across the channel. The War Office would construct the concrete caissons codenamed Phoenix, the floating roadways codenamed Whale, and provide anti-aircraft protection. Once in France, the Army would sink the caissons and assemble the complete harbour. The division of labour established, construction could finally begin. The scale of the project dwarfed anything Britain had attempted. From the summer of 1943, construction began in earnest, employing up to 45,000 personnel simultaneously across dozens of sites. The concrete caissons alone represented an engineering marvel. The largest Phoenix units measured 200 feet long, 60 feet high, and weighed more than 6,000 tons when complete. A total of 213 caissons of various sizes would be required, consuming more than 1 million tons of reinforced concrete and 70,000 tons of steel reinforcement. Massive excavations were carved from the banks of the Thames and Medway rivers to create the dry docks where Phoenix units could be built. The construction process required precision that seemed impossible given the urgency. Each caisson was essentially a floating concrete box, airtight except for controlled flooding valves that would lower it to the seabed in precise positions. The walls had to be thick enough to withstand Atlantic storms, yet light enough to float during transport. Reinforcing steel had to be positioned with mathematical exactness to prevent structural failure. Concrete had to be mixed, poured and cured under controlled conditions, despite chronic wartime shortages of cement and steel. Commercial construction firms across Britain received contracts for individual caissons. Watts Construction, Balfour Beatty, Henry Boot, Bovis and Company, Costain, John Laying and Son, Peter Lind and Company, Sir Robert McAlpine, Molam, Nuttall and Taylor Woodrow all contributed sections. The firms worked in ignorance of the final purpose. Security demanded that construction workers know only their immediate task, not the grand design. Arthur Warts, managing director of Warts Construction, would recall decades later in a 1970 interview, "Our workers built massive concrete pontoons according to specifications provided by government engineers. We had no idea what they were for." The rumour circulating among the men was that these were somehow related to post-war housing construction. When a senior officer from Whitehall visited our yards and saw how puzzled everyone looked, he reassured us that our work was vitally important for the war effort. Only after D-Day did we learn we'd been building sections of artificial harbours. The floating roadways presented equally daunting challenges. Alan Beckett's design called for steel bridge spans 80 feet long, mounted on floating pontoons made of either steel or concrete called beetles. The bridges had to be flexible enough to accommodate tidal variations of up to 20 feet, while rigid enough to support fully loaded trucks. The solution involved a torsionally flexible joint system that allowed each span to twist independently while maintaining continuous roadway surface. 16 kilometres of these whale roadways would be manufactured, each section precisely engineered to connect with its neighbours. The pierheads, where ships would actually dock, received the code name Spud. Each consisted of a massive pontoon with 4 legs that rested on the seabed, while the pontoon floated up and down with the tides. Hydraulic systems allowed the legs to extend or retract as tidal conditions changed, maintaining constant deck height relative to docked ships. The engineering tolerances were measured in fractions of an inch over structures weighing hundreds of tons. Testing became crucial. The Scottish harbour at Garliston in Wigtown Bay offered characteristics similar to the Normandy beaches. Flat, sandy, remote, and sparsely populated, it provided perfect conditions for full-scale trials. A security cordon was established around the entire area. Local inhabitants were evacuated under wartime emergency powers. The whole area from Garliston through to the Isle of Wythorn was declared off-limits. A military camp was constructed at Cairnhead to accommodate hundreds of engineers and support workers who would test and refine the Mulberry components. The tests revealed numerous problems that would have proven catastrophic if discovered only on D-Day. Early floating roadway designs collapsed under the weight of a 7-ton truck when subjected to realistic wave action. Swiss roll-type flexible roads washed away entirely during a storm that hit the test site. Hippo pontoons undermined in the sandy bottom, causing crocodile bridge spans to fail structurally. Only Beckett's whale design survived the storm undamaged, leading to its adoption for the final harbour. The bombardons, massive floating breakwaters fabricated from steel and rubberized canvas, underwent extensive modification after test failures. Original designs called for hemp rope connections between individual bombardon units. Testing showed the ropes parted under storm conditions, allowing the huge structures to drift into the inner harbour, where they could cause catastrophic damage. New steel cable connections with redundant safety systems replaced the rope after repeated test failures. Security surrounding the project approached paranoia. The codename Mulberry was selected specifically because it revealed nothing about the project's nature. It was simply the next available designation in a long list of randomly selected codenames. All written communications referred only to Mulberry, never to artificial harbours or floating ports. Workers at construction sites signed Official Secrets Act declarations. Photographs of the components were strictly forbidden. Intelligence services monitored conversations in pubs near construction yards, alert for any loose talk. German aerial reconnaissance posed a constant threat. Luftwaffe planes photographed southern England regularly, searching for evidence of invasion preparations. The Phoenix caissons proved impossible to hide once construction began, as they were simply too large. The cover story claimed they were experimental anti-submarine barriers to be deployed in the English Channel. German intelligence apparently accepted this explanation, as no special preparations were made to counter artificial harbours. An extraordinary security breach nearly exposed the entire project. In May 1944, just weeks before D-Day, the Daily Telegraph crossword puzzle began including words directly related to Operation Overlord. On consecutive days, clues led to solutions including Utah, Omaha, Juneau, Sword, Gold, the names of the 5 invasion beaches, and most alarmingly, Mulberry itself. MI5 immediately investigated Leonard Dorr, the headmaster who compiled the Telegraph crossword. Intensive interrogation revealed that Dorr often asked students for interesting words to include in his puzzles. Many of those students lived near US military barracks where Overlord planning was underway. The words had entered Dorr's vocabulary through casual conversation overheard by students and repeated innocently. MI5 concluded the appearance of classified operation names was indeed coincidence, though an unnerving one. The investigation continued until after D-Day to ensure Dorr wasn't a German agent using an impossibly subtle communications method. By June 1944, the artificial harbours existed as thousands of individual components scattered across southern England. The logistics of moving them to assembly points, then across the Channel, then into final position off the Norman coast boggled the mind. 2 complete harbours had been constructed. Mulberry A would support American forces landing at Omaha Beach near Saint-Laurent-sur-Mer. Mulberry B, also called Port Winston in honour of Churchill, would support British and Canadian forces at Gold Beach near Arromanches. Each harbour required approximately 600,000 tonnes of concrete and prefabricated steel. The components included 213 Phoenix caissons of various sizes, 10 miles of whale floating roadways, 33 pier heads, 70 obsolete merchant ships to be scuttled as additional breakwaters in positions codenamed gooseberries, and 24 massive bombardment floating breakwaters for outer protection. Moving this artificial fleet required 150 ocean-going tugs specially modified for long-distance towing. The tugs were distinguished by large M letters painted on their funnels. Crews took fierce pride in their assignment, understanding they were part of history's most ambitious engineering project. The towing operations alone presented staggering complexity. Phoenix caissons had to be towed at speeds not exceeding 4 knots to prevent structural damage. The journey from English assembly points to the Normandy coast would take 2 days under ideal conditions. Weather predictions became crucial. Rough seas could damage delicate components or part the tow cables. The tugs had to navigate mine-infested waters while maintaining station in massive convoys. Royal Navy minesweepers worked ahead of the Mulberry convoys, clearing lanes through defensive minefields laid months earlier. June 4, 1944, brought the first movement orders. Sections of the Mulberry Harbors began to be towed behind tugs and positioned mid-channel, awaiting the invasion that had been scheduled for June 5th. Then weather intervened. A massive storm system swept across the channel, forcing postponement. The Mulberry components wallowed in rough seas for 24 hours, while Eisenhower agonized over whether to proceed or delay further. When Eisenhower finally gave the order to launch Overlord on June 6th, the artificial harbour components were already at sea. In the pre-dawn hours of D-Day, while Allied soldiers stormed ashore under withering German fire, the first elements of the Mulberry Harbors were being towed into position. The operation proceeded with choreographed precision, despite the chaos of the largest amphibious assault in history. On D+1, June 7th, the first Phoenix caissons were brought into position about a mile offshore from both Omaha and Gold Beaches. Powerful harbour tugs manoeuvred the massive concrete structures with remarkable delicacy, nudging them into precise positions marked by buoys laid down by Royal Navy survey ships days earlier. The controlled flooding of the Phoenix caissons demonstrated the brilliance of their design. Each caisson had multiple chambers with individual flood valves. Engineers could flood specific chambers to achieve exact positioning and orientation before settling the structure to the seabed. The process required hours of careful work for each caisson, but the results justified the effort. As the Phoenix breakwater took shape, it created sheltered water where ships could anchor safely. Simultaneously, 70 obsolete merchant ships moved into position for scuttling. These vessels, codenamed corncobs and collectively creating the Gooseberry breakwaters, had been assembled at Oban on Scotland's west coast months earlier. Stripped of everything valuable, ballasted for precise buoyancy, and fitted with scuttling charges, they made their final voyage under their own steam. At predetermined coordinates off the invasion beaches, the crews opened seacocks, detonated charges, and abandoned ship. The vessels settled to the bottom in carefully planned positions, creating an outer line of protection against the Atlantic swells. At Utah Beach, 10 ships went down, including the Benjamin Conti, David O. Sailor, George S. Wasson, and Victory Sword. At Omaha Beach, another formation of corncobs established the outer perimeter of Mulberry A. The scuttling operations proceeded so smoothly that most ships settled within 50 feet of their assigned positions, a remarkable achievement given the complexity of deliberately sinking a ship exactly where intended. The whale roadways came next. Long trains of linked pontoons and bridge spans snaked across the channel, towed by dedicated tugboats. Once in position, Royal Engineers secured them to the spud pierheads and extended them toward shore. The flexible joints that Beckett had designed proved their worth as the roadways undulated with the waves while maintaining structural integrity. By June 13th, Mulberry B at Arromanches had developed sufficiently to provide 2 crescent-shaped harbours capable of accommodating up to 75 Liberty ships and smaller craft simultaneously. The speed of construction astonished even the engineers who had planned it. Within just 7 days of the D-Day landings, both artificial harbours were beginning to handle cargo. The first supply ships to use the Mulberry facilities found themselves in the strange situation of docking at piers that hadn't existed 10 days earlier, in harbours built from materials that had been scattered across England 2 weeks before. Ship captains accustomed to traditional harbours marvelled at the ingenuity. Captain James Morrison of the Liberty ship Robert E. Peary wrote in his ship's log, "Approached what the charts show as open beach, instead found complete harbour facilities including floating piers, breakwaters and navigational markers. Docked at Pier 7 of Arromanches Harbour and discharged 400 tons of ammunition, 200 tons of rations and 150 vehicles in 8 hours. The entire facility floats on the tide, rising and falling 15 feet between high and low water, yet remains perfectly functional throughout. The engineering involved defies my comprehension." Then disaster struck. On June 19, 1944, the worst June storm in 40 years descended on the English Channel. For 3 days, northeasterly winds of force 6 to force 8 pounded the Normandy coast. Waves reaching 8 feet in height crashed against the artificial harbours. The bombardon outer breakwaters, designed to absorb such punishment, began to fail. Some broke apart under the pounding. Others tore free from their anchors and drifted into the inner harbours, where they smashed into Phoenix caissons and whale roadways. At Omaha Beach, Mulberry A suffered catastrophic damage. The harbour had not been fully completed when the storm arrived. Critical reinforcements and anchor systems were still being installed. Phoenix caissons cracked under the wave assault. Whale roadways broke free and washed onto the beach in tangled wreckage. By the time the storm abated on June 22nd, Mulberry A was beyond repair. The American decision to abandon Mulberry A came quickly. Surveys showed that restoring the harbour would take longer than building it originally, as damaged components would first need to be removed. Instead, the Americans salvaged usable sections and sent them to reinforce Mulberry B at Arromanches. The British harbour, more protected by the natural geography of Gold Beach and more completely assembled before the storm, survived with damage but remained functional. Mulberry B was substantially reinforced with units salvaged from the American harbour. The Phoenix caissons were pumped full of sand to give them greater stability, a measure that undoubtedly explained the extended service which the British port rendered. The storm validated the Mulberry concept even as it destroyed one of the harbours. At Omaha Beach, where Mulberry A lay in ruins, the gooseberry breakwater created by scuttled ships had held firm. Ships anchoring in the protected water behind the block ships rode out the storm with minimal damage. Without even that basic protection, the June storm would have scattered the invasion fleet and potentially doomed the entire operation. Lieutenant Colonel George Shattuck, commanding 20 Port Group Royal Engineers responsible for operating Mulberry B, wrote in his after-action report, "The storm of June 19th to 22nd subjected our harbour to conditions far exceeding design specifications. That any portion survived testifies to the quality of British engineering and the foresight of our planners. The bombardons which failed did so while absorbing punishment that would have destroyed the entire invasion fleet had those ships been exposed to open water. Even in failure, the Mulberry concept proved its value. The loss of Mulberry A forced the Americans to rely on direct beach landing of supplies, a technique they refined to unexpected levels of efficiency. By early July, Omaha Beach was handling 12,000 tons daily despite lacking a harbour, an achievement that surprised everyone, including the planners. Yet this success depended on the gooseberry breakwater, a Mulberry component. Mulberry B at Arromanches continued operating long past its design life. The harbour was intended to function for just 3 months, sufficient time to capture and restore the port of Cherbourg. Instead, Port Winston remained operational for 10 months after D-Day. The statistics of what this single artificial harbour accomplished defied belief. Through Port Winston passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. At peak efficiency, the harbour was landing 7,000 tons of equipment and supplies daily. The port operated around the clock, with ships docking at any hour to discharge cargo. The whale roadways proved their worth beyond anyone's expectations. Designed for a 3-month lifespan, they handled traffic constantly for 10 months. Fully loaded trucks drove from Liberty ships anchored offshore directly onto French soil across bridges that floated on the tide. Many of these bridge spans found second lives after the war, repaired and used to replace bombed bridges across France, Belgium, and the Netherlands. Examples remain visible to this day, including a span over the Noiro River in Normandy and another crossing the Moselle River between Cattenom and Königsmacker. The German reaction to the Mulberry Harbors revealed the complete failure of their military intelligence and strategic thinking. German commanders had based their entire defensive strategy on the assumption that the Allies would need to capture a port. Rommel had fortified Cherbourg, Le Havre, and other harbours precisely because he believed invasion forces could not survive without them. The Atlantic Wall, with its millions of mines and thousands of concrete bunkers, was positioned primarily around port facilities. When Allied forces came ashore on beaches rather than ports, German intelligence initially interpreted this as evidence of a limited raid rather than a full invasion. Even when the scale of the landings became apparent, German commanders assumed the Allies would rapidly move to capture Cherbourg. The appearance of artificial harbours off the invasion beaches shocked the German High Command. They had no intelligence warning of the Mulberry project despite its massive scope. The concept violated German assumptions about what was militarily possible. Their disbelief bought the Allies precious time to consolidate the beachhead. Albert Speer, Nazi Germany's Minister of Armaments and War Production, would later provide the most eloquent testament to the Mulberry Harbour's impact. After the war, during interrogation and later in his memoirs, Speer reflected on the Atlantic Wall's failure. His words, though coming from an architect of Nazi war crimes, captured the essence of why Germany lost. To construct our defences in 2 years, we used 17 million cubic metres of concrete and 1.2 million tons of steel. A fortnight after the landings by the enemy, this costly effort was brought to naught by an idea of simple genius. The simple genius Speer referenced was the Mulberry concept. Germany had invested enormous resources into fortifying every port along the Atlantic coast. The Nazi High Command believed these fortifications made invasion impossible without catastrophic Allied casualties. Instead, the Allies simply bypassed the fortified ports entirely, bringing their own harbours with them. This represented more than a tactical surprise. It demonstrated a fundamental difference in how the two sides approached warfare. German military thinking remained rooted in 19th-century concepts of fortress warfare and defence of strong points. The Allies embraced innovation, willing to attempt solutions that conventional wisdom deemed impossible. The contrast extended beyond the Mulberry Harbors to encompass Allied strategy as a whole. While Germany relied on static defences and counterattacks with armoured reserves, the Allies developed specialised equipment to overcome obstacles. Hobart's Funnies, a collection of modified tanks including flail tanks for clearing mines, bridge-laying tanks for crossing obstacles, and amphibious tanks for swimming ashore, epitomised this innovative approach. The Germans had technical brilliance, as evidenced by weapons like the V-2 rocket and jet aircraft. But they lacked the industrial capacity and strategic flexibility to turn technical innovations into war-winning advantages. The Allies, particularly the United States and Britain working together, combined innovation with industrial mass production. The Mulberry Harbors exemplified this combination. The engineering innovations from Beckett's flexible roadways to the Phoenix caissons controlled flooding systems represented cutting-edge design. Yet the project succeeded because British industry could manufacture these innovations in quantity despite 4 years of total war. Over 45,000 workers contributed to Mulberry construction simultaneously. Commercial firms across Britain diverted resources from other war work to produce components. The scale of coordination required dozens of government ministries, military services, and private companies to work in unprecedented cooperation. This organizational achievement matched the technical accomplishment. Consider the Phoenix caissons alone. Building 213 massive reinforced concrete structures, each weighing thousands of tons, required more concrete than most nations produced in an entire year. The construction sites had to be created from scratch along riverbanks. Raw materials, cement, steel, aggregates had to be allocated despite desperate shortages. Transport to assembly points required specialized equipment and careful scheduling. Quality control had to ensure every caisson could survive ocean towing and storm conditions. The towing operation itself deserves recognition as a maritime achievement. Moving 600,000 tons of concrete and steel across 30 miles of open water while maintaining precise positioning and timing stretched naval capabilities to their limits. The 150 tugs involved in Operation Mulberry represented a significant portion of Britain's entire tug fleet. Many were commercial vessels pressed into military service. Crews received minimal training on towing oversized loads through minefields and enemy-controlled waters. Yet the loss rate during the cross-channel towing operations remained remarkably low. Only a handful of Phoenix caissons were lost during transport, and most of those were damaged in the June storm rather than during the actual channel crossing. The human side of the Mulberry story deserves equal attention with the technical achievements. Colonel V.C. Steer Webster, a Royal Engineer who played a leading role in the invention, design, development and trials of all Mulberry equipment, left behind an extensive archive now housed at McMaster University in Canada. His papers reveal the intense pressure engineers worked under as D-Day approached. Steer Webster's diary entries from March through May 1944 document the frantic pace. March 15, 1944. Churchill visited the whale testing facility today. He wanted to personally walk across the floating roadway to satisfy himself it would support loaded trucks. After watching vehicles cross successfully, he turned to me and said, "Steer Webster, if this damned thing works as well in France as it does here in England, you chaps will have earned the nation's eternal gratitude. The immense weight of responsibility we carry becomes more real with each passing day." April 3, 1944. Received word that 2 Phoenix caissons developed cracks during towing trials. Immediate investigation reveals the reinforcing steel was improperly positioned at the construction yard. All similar units must now be inspected. This delay could push back the entire invasion if we cannot resolve it within a week. Sleep has become a rare luxury. May 20th, 1944. Final preparations underway. The sheer scale of what we've built staggers belief. If someone had proposed this scheme to me 3 years ago, I would have declared it impossible. Yet here we stand, having turned impossibility into imminent reality. God help us all if it fails. The personal accounts from Royal Engineers who operated the Mulberry Harbors in France provide ground-level perspective on the achievement. Sapper William Hutchinson, attached to 20 Port Group, wrote to his family in July 1944. "We work 18-hour days keeping Port Winston operational. The harbour lives and breathes like a great mechanical beast. With each tide, the entire structure rises 15 feet and falls again. We must constantly adjust moorings, inspect pontoons for damage, repair roadway sections, and guide ships to pierheads. German artillery occasionally shells us from inland positions. Luftwaffe raids occur nightly, yet the supplies flow without pause. Today alone we unloaded 40 ships carrying tanks, ammunition, rations, fuel and medical supplies. Everything an army needs arrives through our floating harbour. When I think that this entire port didn't exist a month ago, that we assembled it under fire from components towed across the channel, I can scarcely believe I'm part of it. Merchant Navy crews delivering supplies through Port Winston expressed amazement at the facility. Captain Robert Fraser, master of the Liberty ship John P. Holland, filed a report with his shipping company after his third voyage to Arromanches. Approached the French coast expecting to anchor offshore and light a cargo to the beach in small craft, the standard procedure for unimproved harbours. Instead received orders to proceed directly to Pier 11 in Port Winston. The entire harbour, consisting of breakwaters, floating piers and navigational aids, appeared as substantial as any permanent installation I've docked at in 20 years at sea. The engineering required to create this facility from nothing, to anchor it against channel tides and storms, and to maintain it under combat conditions, represents an achievement that will be studied for generations. We discharged 500 tons in 6 hours and departed to make way for the next ship. The efficiency rivals peacetime operations at established ports. The impact of the Mulberry Harbors on the Normandy campaign's outcome cannot be overstated. Without them, the Allies would have faced 3 choices, all dire. First, accept massive casualties capturing a fortified port like Cherbourg immediately after D-Day, when forces were weakest and German resistance strongest. Second, rely entirely on beach landings for supplies, exposing the invasion fleet to weather that could destroy the entire operation as the June storm demonstrated. Third, delay invasion indefinitely while seeking an alternative that might not exist. The Mulberry solution eliminated these impossible choices. It provided the Allies with harbour capacity equivalent to a major port without the casualties of assault or the vulnerability of open beaches. The harbours handled sufficient tonnage to sustain the build-up of forces in Normandy during the critical first months. By the time Cherbourg fell to American forces on June 26, 1944, the immediate crisis had passed. The Allies had established an unshakable foothold in France. Even when German demolitions left Cherbourg unusable for weeks, the advance continued because Port Winston maintained supply flow. The strategic implications extended beyond Normandy. The success of the Mulberry Harbors fundamentally altered Allied amphibious doctrine. After D-Day, planners no longer assumed they needed to capture a port immediately. Future invasions could land on any suitable beach, knowing that artificial harbour techniques could sustain operations until permanent ports were captured and restored. This flexibility gave the Allies enormous advantages in choosing landing sites. They could select beaches based on defensive weakness rather than proximity to ports. German commanders could no longer concentrate defences around harbours, knowing the Allies might land anywhere along thousands of miles of coastline. The paranoia this induced forced Germany to spread forces thinly, rather than concentrating them at decisive points. Plans were drawn up to use Mulberry technology for the eventual invasion of Japan. Engineers were dispatched to the Pacific Theatre to survey potential landing beaches and assess construction requirements. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 rendered these plans moot, but the preparation demonstrated how thoroughly the Mulberry concept had been embraced as standard Allied procedure. No similar wartime engineering feat has been attempted since 1944. The combination of technical innovation, industrial-scale production, security, logistics, and operational deployment under fire remains unique in military history. Modern militaries studying amphibious operations still examine the Mulberry Harbors as a case study in solving impossible problems through engineering ingenuity. The physical remains of Port Winston survive to this day at Arromanches. Phoenix caissons still visible at low tide mark the outer breakwater. Local fishermen use them as landmarks for navigation. Tourists visiting the D-Day beaches can see the concrete evidence of what Allied engineers accomplished in 1944. Several Phoenix caissons dot the British coastline as well, monuments to construction problems and testing failures. At Pagham Harbour in West Sussex, a caisson known as the Near Mulberry sank during towing and could not be refloated. It remains visible at low tide, scheduled as a protected historic monument. Another caisson, the Far Mulberry, broke its back in a storm the night before D-Day and lies in deeper water offshore. At Thorpe Bay, near Southend-on-Sea, a phoenix being towed from Immingham to Southsea began leaking and was intentionally beached on a sandbank in the Thames estuary. It too achieved scheduled monument status, accessible at low tide for those willing to wade through mud to examine its construction. These failures, preserved accidentally as monuments, remind us that the Mulberry project involved considerable risk. Not every component performed as designed. Not every caisson reached France intact. The June storm destroyed one complete harbour and damaged the other. Yet the project succeeded because British and American engineers had built in redundancy, created multiple solutions for critical problems, and adapted quickly when initial designs failed. The long-term impact of the Mulberry Harbors on civil engineering deserves recognition. The innovations developed for military necessity found peacetime applications. Floating bridge technology advanced significantly thanks to Beckett's whale design. Post-war harbour construction incorporated lessons learned about breakwater design and tidal accommodation. Concrete mixing and curing techniques developed to produce the Phoenix caissons under wartime pressure improved commercial construction practices. Perhaps most importantly, the Mulberry project demonstrated that massive engineering projects could be completed in months rather than years when urgency demanded. The organisation, planning and execution skills developed during Mulberry construction influenced post-war infrastructure projects worldwide. The personnel involved in building the artificial harbours dispersed after the war into commercial construction, bringing with them experience in managing complex projects under severe constraints. The recognition given to Mulberry engineers came slowly. Wartime secrecy kept details classified for years after 1945. The engineers themselves, modest by nature and training, rarely sought publicity. Steer-Webster's archive remained private until donated to McMaster University in 1976. Hugh Ioris Hughes received no public honours during his lifetime, despite his fundamental contributions to the harbour design. Alan Beckett, whose whale roadways proved crucial to Mulberry's success, continued his engineering career in obscurity. Only decades later did historians begin recognising the scale of achievement represented by the artificial harbours. The Institution of Civil Engineers included the Mulberry Harbors among the 200 projects celebrated during its 200th anniversary in 2018. Scholarly studies examined the technical and organisational aspects of the project. Documentaries brought the story to wider audiences. Military historians acknowledged that D-Day's success depended as much on engineering innovation as military valour. The contrast between Allied and German approaches to the invasion problem crystallised in the Mulberry Harbors. Germany chose the obvious solution: fortify the ports so heavily that capture becomes impossible. The Atlantic Wall, with its millions of tons of concrete and elaborate defensive systems, represented conventional military thinking applied with German thoroughness. The Allies chose the unobvious solution: make ports irrelevant by creating new ones where needed. This required believing the impossible could become possible through engineering and industrial effort. It required leaders willing to authorize enormous expenditures on an unproven concept. It required engineers willing to attempt what their training said couldn't be done. It required construction workers toiling in ignorance to build components they didn't understand for purposes they couldn't imagine. The difference in mindset explains why the Allies won. German military culture valued obedience, hierarchy, and adherence to proven methods. This produced excellence in execution, but rigidity in planning. When Allied actions violated German assumptions, the command structure struggled to adapt. Allied military culture, particularly Anglo-American cooperation, valued innovation, flexibility, and pragmatic problem-solving. This sometimes produced chaos and inefficiency, but it allowed rapid adaptation to changing circumstances. When conventional solutions proved inadequate, Allies sought unconventional alternatives. The Mulberry Harbors embodied this cultural difference. A German general presented with the harbour problem would have calculated forces needed to capture Cherbourg and accepted the casualties. An Allied general authorised building floating cities to bypass the problem entirely. On the 40th anniversary of D-Day in 1984, a group of surviving Mulberry engineers gathered at Arromanches to reflect on their achievement. The reunion included British and American participants, military and civilian contributors, designers and construction workers. Their reminiscences, recorded by the Imperial War Museum, provide a fitting conclusion to the Mulberry story. Sir Bruce White, who supervised much of the construction, spoke at the reunion dinner. "We were young men facing an impossible task. Build a harbour that can be assembled in days, that can float yet withstand Atlantic storms, that can handle more cargo than Dover while anchored to sand rather than bedrock." Every engineering principle we'd learned said it couldn't be done, yet we had no choice. The invasion depended on solving these impossible problems, so we stopped thinking about why it couldn't work and focused on making it work. We tested, failed, modified, and tested again. We manufactured on a scale that strained Britain's industrial capacity. We towed floating concrete boxes across mined waters. We assembled harbour components while German artillery shells fell around us. And it worked. Not perfectly. We lost Mulberry A in the June storm. Many components failed. Constant repairs were needed. But it worked well enough. Port Winston kept the supplies flowing. The harbour bought us time to capture Cherbourg. That time made the difference between victory and defeat. Alan Beckett, whose Whale roadways had proven crucial, offered his perspective. "I was a young lieutenant in the Royal Engineers when they assigned me to solve the floating roadway problem. The requirements seemed contradictory. Must be flexible enough to accommodate 15-foot tidal variations. Must be rigid enough to support loaded lorries. Must be durable enough to last months in salt water. Must be simple enough to manufacture quickly. Must be transportable across the channel." Each requirement alone posed significant engineering challenges. Together, they appeared insolvable. I spent weeks sketching designs, building small models, testing them in a laboratory. The breakthrough came from watching a snake move across sand, its body flexing at multiple points while maintaining overall forward motion. I realized the roadway needed similar characteristics, rigid within each span but flexible at the joints. The torsional flexibility proved to be the key innovation. Once we had that principle established, the detailed engineering followed. Seeing the Whale roadways still functioning at Arromanches 10 months after D-Day, handling traffic far exceeding their design capacity, gave me greater satisfaction than any other engineering work I've done. An American civil engineer who had worked on Phoenix construction spoke about the industrial achievement. People focus on the technical innovations, and rightly so. But the manufacturing process deserves equal recognition. We built 213 massive reinforced concrete structures in 8 months, while Britain was fighting a total war. Every resource was scarce. Cement, steel, timber, labour, transport. Everything was needed for a dozen other urgent priorities. Yet the Mulberry project received what it needed because Churchill and Eisenhower understood its importance. The coordination required was staggering. Concrete had to be mixed to precise specifications. Steel had to be fabricated and positioned within millimetre tolerances. Caissons had to be built in dry docks created from scratch along riverbanks. Then we had to flood the dry docks, float out multi-thousand-ton concrete boxes, and tow them to assembly points without structural failure. That we accomplished this at dozens of locations simultaneously, while maintaining absolute secrecy, while German bombers raided nightly, speaks to the determination of everyone involved. From the humblest labourer to the most senior engineer, everyone understood they were building something that would change the course of history. A Royal Navy officer who had commanded one of the tugs towing Phoenix caissons across the channel shared his memories. The crossing took 2 days at our maximum safe speed of 4 knots. We towed Phoenix Unit 47, one of the larger caissons weighing over 6,000 tons. The tow cable was thick as a man's arm, yet I watched it stretch tight with the strain. We navigated through mine-swept channels marked by buoys that German E-boats tried to remove. We maintained station in a massive convoy while avoiding collisions with other tows. The entire channel was filled with ships, thousands of them, all heading for Normandy. When we reached our assigned position off Omaha Beach, we held station while engineers flooded the Phoenix in a carefully controlled sequence. It took 6 hours to sink that massive caisson into precise position. Then we cast off and returned to England for another tow. My crew made 4 round trips in 10 days. We were exhausted, running on tea and determination, but we never questioned the importance of our work. The reunion concluded with a visit to the beaches where Mulberry B had stood. The participants, now elderly men, walked across sand where artificial harbour components had once created a bustling port. Phoenix caissons offshore marked the ghost of Port Winston. Some of the engineers wept, remembering comrades who hadn't survived the war, thinking about the magnitude of what they had achieved in 1944. One participant summarised the feelings of all present. We came to France 40 years ago as young engineers tasked with the impossible. We were told to build a harbour where none existed, to create shelter from storms using concrete and steel, to sustain an invasion with facilities assembled in days. We were frightened we would fail, terrified our failure would doom the men storming these beaches. Instead, we succeeded beyond our own expectations. Port Winston worked, the supplies flowed, the invasion held. We helped win the war. Looking back across 4 decades, I feel immense pride in what we accomplished. We proved that engineering ingenuity, industrial capacity and determination could solve problems that conventional wisdom declared impossible. The Mulberry Harbors were our answer to Hitler's Atlantic Wall. Concrete and steel versus concrete and steel. But our concrete floated. Our steel bent with the tides. Our harbour went where it was needed rather than waiting for the enemy to attack it. In that flexibility, that innovation, that refusal to accept the limitations others imposed, we found victory. The German High Command had dismissed the possibility of invasion without ports. They had fortified every harbour from Norway to Spain, confident that Allied supply requirements made capture of a major port inevitable and early. They calculated that defending ports was sufficient to prevent invasion. The Germans were wrong. Americans built a harbour from scratch overnight, or more precisely, built 2 harbours in England over 8 months, transported them across the Channel in 3 days, and assembled them into functioning ports within 2 weeks. The feat was impossible by every conventional measure. It required engineering innovations that didn't exist when the project began. It demanded industrial production that stretched British capacity to the breaking point. It needed organisational coordination across dozens of agencies and companies. It meant transporting and assembling harbour components while under enemy fire. Yet it worked. The Mulberry Harbors stand as testament to human ingenuity, to the power of innovation over conventional thinking, to the triumph of flexible problem-solving over rigid doctrine. When faced with a strategic problem that seemed to have no solution, Allied planners refused to accept impossibility. They instead asked how engineering could create a solution that changed the rules of warfare itself. The artificial harbours of Normandy represent the ultimate expression of the arsenal of democracy, the marriage of technical innovation and industrial capacity that characterised Allied victory in the Second World War. More than the battles fought, more than the heroism displayed, more than the tactics employed, this willingness to attempt the impossible and make it reality decided the war's outcome. The Germans fortified what existed. The Allies created what was needed. In that difference lay the seeds of D-Day's success and Nazi Germany's ultimate defeat.